So in 17, then the first thing that we need to talk about is electric charge. So the big idea here is essentially now, well, what is charge? And what you get is that charge is essentially a fundamental property of matter. Okay. And I think when we say that, I don't know if a lot of things kind of come to mind with that type of statement. But what we can talk about is essentially, well, what is matter? What do y'all think? What is matter? Or what do we know about matter? Surely we know something, right? Sure. That's a good one. Something that takes up space. What about the composition? This is kind of more where I would like to go. Yeah, I would agree that matter is a physical quantity, you know. Well, actually, matter can be destroyed, and it can be created in what they call pair production and annihilation, but that's just a funky kind of thing. So Aliana's got what I was hunting for, is that it's made up of atoms. And Crystal's got a good point that it has mass. And what we're going to get is that charge is essentially like mass. It's a similar kind of thing. I mean, it's different, but again, it's one of those properties of matter kind of things. And in terms of composition, then what you get is that matter is made up of atoms. And what do we know about the composition for atoms? Yeah, they're made out of protons, neutrons, and electrons. That's exactly what I'm looking for. And then they usually draw these kind of pictures to represent our atom. And so what we have here is that this is going to be the nucleus, which was named after the biological nucleus. The ones with the little plus sign, these are going to be our protons that I drew in red. And then the ones that are in green with no sign, these are the neutrons. Okay. And together, they could refer to these as nucleons. So particles within the nucleus. So we find our protons and our neutrons in the nucleus. And then somehow, some way, we have electrons, orbiting about the nucleus. And, we're not going to go into a lot of detail about that, but I'll just draw it like we standardly picture, like, planets orbiting the sun type of thing, which is not really our current state of understanding. If you do took chemistry and you talk about electron clouds, then that's a bit more, it's closer to our current state of understanding that we have. But the thing is that when we have this kind of diagram here, it bothers me greatly because it is horribly not to scale. If we come in and look at this, then the size of the nucleus is on the order of 10 to the minus 15 meters, and then the size of the atom itself is on the order of 10 to the minus 10th meters. And if we were to go in and take a look at the ratio of these two things, then we get that, 10 to the minus 15 meters compared to 10 to the minus 10th meters. Then what you get out of this is 10 to the minus 5, okay? And so what this is telling us is, even though it's negative, that doesn't matter, is that this is, 5 orders of magnitudes worth of difference in size. Okay, and so if we go back to our handy ruler here, then we can see that this is a centimeter and the little ticks are millimeters, and that there are 10 millimeters in a centimeter. Maybe we should have done it over here where it's a little clearer to see. And so that's 10 to the 1, which is 1 order of magnitude. Now, if I had a meter stick, which I don't, then there would be 100 centimeters in the 1 meter, and that's 2 orders of magnitude. That's 10 to the 2, because 10 to the 2nd power is 100. And there would be 1,000 millimeters in the meter stick, which is, again, about waist high. It's about a yard, pretty close. And that's only 3 orders of magnitude. We need 5. Okay. So what I usually argue is that if we scale the nucleus at about a centimeter, then it's 2 orders of magnitude to the meter, and we need 3 more orders of magnitude to get 10 to the 5, and so 10 to the 3 meters is a kilometer. So what I'm telling you is that if we scaled the nucleus at about a centimeter across, the atom itself would be a kilometer across. And the one I drew here is really about 2 centimeters across, and so my atom should really be 2 kilometers across. It wouldn't fit in this room. It wouldn't fit on my property. It's horribly not to scale. Oh, 10 to the minus 15. So this one's 10 to the minus 15. And this one's 10 to the minus 10. Okay. All right. Go. And so, like I said, the diagram is horribly not to scale. And so that's not really the, that's not as great. But it's as far as what they would call a toy model, as a simple model, we can get really pretty far with this particular piece. And so now what I want to point out is that really out of these particles that make up the atoms that make up the matter, okay, technically only the electrons are fundamental. You get picky about it. What we mean by that is that the electrons are not made up of any smaller pieces. The protons and the neutrons themselves are made up of smaller parts called quarks, but quarks are kind of funny, and that you can't get an individual quark all on its own. And because of that, we kind of treat protons and neutrons as fundamental. It's not terribly far off. It's not too wrong per se, I guess you could say. Okay. And so then when we look at this, the electrons themselves and our current state of understanding are fundamental particles. They're not made of smaller pieces. They're a class of particle called a lepton. And like I said, There's no real smaller pieces. And so now what we can look at is we can go in and talk about the properties of that fundamental particle of the electrons. And very often they'll note it as an E with a little minus sign on here. That's the symbol they pretty often use for electrons. And so then the first property that we can look at is going to be mass. Okay. And what we find is that the mass of an electron is 9.11 times 10 to the minus 31 kilograms, so in SI units. And we also have additional properties of the electron. We can talk about the charge. The symbol that they tend to use for charge is AQ. And so we'll put our little electron symbol down there. So the charge of the electrons, how you would interpret that. This will be negative by convention. So 1.602 times 10 to the minus 19 coulombs. And then there's a third property called the magnetic moment. Now, you could also talk about, instead of the magnetic moment, we could talk about the spin. But if you have a charged particle with spin, then it has a magnetic moment. So you get to kind of pick a little bit, but most likely what you've talked about if you've had chemistry is spin of the electron. But we're going to focus more on but again, a spinning charged particle has a magnetic moment. We're going to look at the magnetic moment instead. And that value turns out to be negative 9.28 times 10 to the minus 24th. And this is in joules per Tesla. Okay. And so what we mean by the fact that these are properties of the electron and that the electrons are fundamental particles is that every electron in the universe has exactly this mass, this charge, and that magnetic moment. Every single one of them. They all have exactly the same values. And so this is what we mean by being a property of those particular particles. And then what we can do is we can go in and note that there's a really interesting relationship here between our properties of the electron, which are a fundamental particle that make up all the atoms that make up all the matter, in terms of the relationship to what they call the long-range forces in nature. Okay. And so what you find is that the mass essentially will correspond with our gravitational force. Because what you get is that mass, the gravitational force, is an attractive force between any two particles that have mass. So mass goes hand in hand with the gravitational force, and that our charge corresponds to the electric force. And this is because the electric force is either an attractive or a repulsive force between, any two objects that in general, have a net charge. Since the objects are made up of particles that have the property of charge, then generally what will happen is that most objects have equal amounts of positive and negative charge, and so therefore are electrically neutral. And so if you have an imbalance in those numbers of positives and negative charges, then what you get is that that object becomes charged. So, but the electric force is a force, either attractive or repulsive force between any two objects that have charge or have a net charge on them. And then our last one is the magnetic moment acts like a little compass needle, acts like a magnetic dipole. Okay. And so therefore it's related into the, magnetic force. So the magnetic force is between, any two objects that, behave like magnets. And the electron itself behaves like a magnetic dipole. has a dipole moment, is how they call that. And so this really is not a coincidence. I mean, this is essentially very important. And what you'll find is that the proton has a mass and a charge and a magnetic moment. The neutron has a mass but no charge and a magnetic moment, and so on and so forth. Okay. And so then what we'll find is that these long-range forces, what that implies is that the magnitude of the force is going to be proportional to 1 over the distance squared between the objects that generate the force, between the two masses, between the two charges, between the two objects with magnetic moments, things along those lines. So this is called an inverse square law force. And that's how all these long-range forces behave. Now, just for the sake of completeness, we could add in what they call the nuclear forces in order to complete the fundamental forces in nature. And so what we find is that the electrons have a property called charge, and by convention they're taken to be negative. And what we'll find is that the protons will have an equal but opposite amount of charge that you have on the electrons. And so very often what they will do is they go in and they will define what they call the fundamental unit of charge. What they give is this kind of lowercase e, and it's that 1.602 times 10 to the minus 19, and then the unit for charge is a coulomb. Okay, and so this is our fundamental unit of charge. And so then what that implies is that if we look at the charge on the proton, then this is plus E. And of course, the charge on the electron is minus that value E, which is what we wrote here. So E is just this value here. Or if you like, the charge on the proton is the negative of the charge on the electron. So they have equal but opposite amounts of charge. And so when we come back and we look at our model of the atom, then what you get is that the number of protons in the nucleus determines which element we happen to have. If there's 1, it's hydrogen, 2, it's helium, 3, it's lithium, and so on and so forth. The number of neutrons in the nucleus indicate which isotope or which nuclide we happen to have. And so what we have here is, since there's 2 protons, that's helium, and since there are 4 nucleons, that is helium-4 would be the isotope or the nuclide. And then the 2 protons carry 2 positive units of charge, and the 2 electrons carry 2 negative units of charge. So this particular atom is electrically neutral. And most matter that we run across is generally neutral like this. If you were to go in and remove an electron, then what you would get is it would be ionized, and we would have an excess proton because this plus and minus would balance, and then we were left over with 1 excess positive charge. So it would be positively ionized. And if we were to add an electron, then it would be negatively ionized. If you were to remove a proton, then you transmute the element and it goes from helium down to hydrogen. Okay.